As we continue into the second day, what we have is a new idea of being mutually exclusive. And basically what mutually exclusive means is that the events will not overlap. So if you ever want the probability of things that are one or the other, and there's no overlap, if you think about like a Venn diagram, not even sure if you've learned about Venn diagrams before, but you know how Venn diagrams typically overlap. Well, for this situation, it would be more like this thing or this thing, and there's no connection. Because if there is a connection, you would have to subtract off the pieces that overlap. So the reason why this is still part of the binomial probability is because you get phrases like at least or at most. Things like that. So we have an exercise where Jenna's taking a 5-question multiple choice quiz. Each question has 4 choices, so the probability of success is that 1/4. That means the probability of failure is 3/4. And she just randomly guesses, so no thought process on it could be A, however many A's there were, or they could switch it up. But anyway. The probability she correctly answers at least 4 of those 5. So the probability of being at least 4 would be the same thing as the probability of 4 or the probability of 5. And I use the word or on purpose because we add those two probabilities together. And it's impossible to get 6 questions right when it's a 5-question quiz. So in this situation, remember you want to do, there's 5 questions and we're trying to get 4 correct. Maybe I should have color-coded this. That's okay. I think you can follow. And we want the probability of getting 4 of them correct and 1 of them wrong. So that's for the probability of getting exactly 4. But then we also have the probability of getting 5, which would be 5C5, and we want that 1/4 probability, all 5 to be correct, and then this 3/4 probability to the 0. We want none of them wrong, and add those things together. And at this point, I would probably just go to a calculator. I want you to use a calculator. So hopefully you are on board. There's a lot of arithmetic to getting these things correct. Whoops. Delete that. There we go. 1/4 to the 4th power, arrow over, and then you can just write times 3/4 because to the 1st power is still 1. There we go. And then plus, now this is actually a pretty big waste of time if you do 5C5 because that's just equal to 1, and then 3/4 to the 0 power is equal to 1. So it's actually just faster if you know that this is going to be 1/4 to the 5th power. There you go. So the ending probability is 1 out of 64, or you can change that to a decimal or divide it. 1.6%. It'd actually be faster if you just wrote it all out. 1.5625%. So not very likely that Jenna could just randomly guess and get at least 4 answers correct. Here's another problem it's getting you to do that probability. Now, when I hear the word at most, I think 2 or less, and specifically 2 because of the number right here. So let me write that out first. At most 2, I think about how that's the probability. Could be 0, could be 1, or it could be 2. And so we have a 40% chance of rain, and over the next 7 days, so over a week, we want the probability that it rains at most 2 days. So to do this problem, 7C0, we have a 40% chance of it raining, and we want that to be 0. And remember that then it's a 60% chance of not raining, and we want all 7 of them to be that. So that's just a probability of 0. And with a lot of practice, this comes pretty familiar, if you're not familiar yet, that we don't want it to rain 6 days. That would be this one. I don't want that there, though. Okay, and then 7C2, 0.4% chance, 2 and 0.6% 5 times of sunny weather. And at this point, just go to the calculator. Now remember, there are some shortcuts, like 7C0 will be 1, 0.4 to the 0 power would be 1, so it's actually faster if you just type that in. I'll switch back to that purple. So if you're doing my advice, if you don't understand what I just said, then you can write it all out. This is probably pretty boring just to watch. You don't have to write to the first power either. But this is worthwhile to write out so you could all see the appropriate way of writing it. And hopefully I typed it in correctly. You can leave it as a decimal. If you feel like changing it to a fraction, you can. Apparently it won't let me. So let's just go ahead and write it as 41.99%. And you can round that up to 42%. You know, I'm good, you know, if you do something like that, 42.0. Now, sometimes it's best to do the complement of an event. This is not a complement as if it's a geometry problem. It's a complement is that the probability of an event and its complement, so it's basically like not the event happening. We just have a fancy word for it. They need to add up to be 1. So why would we do that? Is if we have a problem that says we flipped a coin 10 times and we want to get at least 2 heads, would you really want to do the probability of 2 plus the probability of 3 plus the probability of 4 ... plus the probability of 10? I hope I've convinced you that that would be a very daunting task. So how about the complement? Okay, well the complement, and this is just one individual's way of writing it. There's other ways of writing a complement of an event, but this is pretty normal. Just kind of a heads up if you feel like using the internet and looking for other ways of writing the complement, that's fine. Is I would write that the opposite of that would be at most 1 heads. And if that doesn't make sense, I could say it's the probability of 0 and the probability of 1 added together. So how could we find that probability? That would be, let's see, 10 flips combination. We want 0 heads, got a 50% chance of getting a heads, and then a 50% chance of getting tails. But then you have to do the 1, 10C1, 50% chance of getting a heads with a 50% chance of getting a tails. And then you could go to the calculator to get that probability. And again, there's some shortcuts here, like this thing would be 1, this thing would be 1. So it'd be faster if you just did 0.5 to the 10th power and then plus 10C1. I'm going to just go ahead and this takes me forever to type it. I do apologize that this probably is boring. But we should get about a 1.07% chance. So since we did the complement, we can figure out the probability of the event. And let me write it out as the equation up there, because the probability of the event plus the probability of the complement need to add to equal 1, or if you want to write it as 100%. So to me it makes sense, and you can bring the question to class, if you want to move that probability over, you would subtract it. So we're going to subtract over 1.07%, and you could just do 1 minus that answer, and you get a 98.9% chance. So the probability of said event is a 98.9. I'll just go ahead and round it to that. So you could do the same thing if you get at least 1 heads on 4 flips. So what might make sense to do that, if you're getting at least 1, is find the probability of getting no heads, which I'll just do this quickly because I want to keep this somewhat short. It would be 0.5 to the 4th power. That's getting a tails each time. So 0.5 to the 4th power is 0.0625. So the probability of heads being greater than or equal to 1 would be 1 minus that answer. I'll just show it right here, and then I'll just change it to the decimal. So it would be 93.75%. I know it says to the nearest 1/10 of a percent. But if anybody's interested in taking stats, you can just round it to wherever you feel like. 93.8 would be fine. And then we have one more example. I think this is the last one. Yep, where we have a game where we're throwing bags on a board. We have 4 congruent triangles. That means that they're all equal shape, equal size. One of which is painted black. So they pay $3 for the 2 bags and will win if at least 1 bag lands in the shaded area. And we're assuming that the bag has to land on that area. So what's the probability that a bag will land in the shaded area? Since they're congruent, just remember it's geometric probability, which I'm not sure if you've learned. It's still the area of what you want over the area of the total. And so the way I would explain it, and I hope this makes sense, is that the probability of shaded, what we want is the one shaded region, and there's a total of 4 triangles. And since they're all the same size, that should be your probability. So determine the probability that Josh wins the game if he plays it once. So if he just plays it once, what they're trying to get you to do is take the 2 bags, and so you get to throw both bags, and that's what they mean by playing the game once. So it's not going to be the same answer as this previous one. So if you're confused, feel free, like in the homework or on the test, feel free to come to me and ask the question. But what they're trying to say is you win the game if at least 1 lands on the board. So that would be the probability of 1 or the probability of the second one being on the bag, on the board. So that would be 2 throws, combination 1. The probability of a success is 1/4. And then the probability of the failure, 3/4. But then you add to it getting both on the board. So that would be 1/4 to the 2nd power, and then 3/4 would be to the 0 power. But hopefully we've done enough where you've noticed some of these things that are just 1, and it'll save you some time. So as you go to 2 combination, I hope you can do that quickly in your head, that that's just 2 times, what do we got? 1/4 times 3/4. And then plus, the next one, you can just do 1/4 to the 2nd power. So we get 7 out of 16. So that's the probability of just winning 1 game. Well, what if Josh plays 3 games? What's the probability he will win at least 1 time? So this is a little bit different. Now your probability of success is 7/16, and your probability of failure is, what would that have to be? The opposite would be 9/16. And so How about this? I'm at the end of my time, so I'm going to give you the answer. And bring your question to class. It's about 82%.